Okay, so good morning. Hope you had a nice viaggio. Just back from Germany, so if I say something silly, it's because I'm jet lagged today or next week, or I can use that excuse for a month, I think so. Okay. So today we're going to have the last class on OWL. So last couple of times we spoke about OWL and we went into increasing depth. And today we're going to continue on that topic, and we're going to discuss a pretty foundational problem in computer science. It doesn't just relate to OWL, it relates to also logic and knowledge representation and what we can use machines for. So back in the early days of computing, there was this hope that computers could answer all sorts of questions for us, and we could just put in a bunch of information or data, and it would be able to reason about the world. However, that's not the case. So when we develop ontologies for knowledge representation like OWL, eventually we reach the limits of decidability, which means what a computer can or cannot do. Yeah, so there are certain things we cannot implement. And the last time we spoke about the tiling problem, and we mentioned how it was undecidable. So just as a brief reminder, the idea is we have some tiles of certain colors, some certain limited finite number of colors. Given the colors, and we have a potentially infinite number of pieces for each color. What we want to say is if there exists an infinite tiling or not. And what are the rules of the tiling? The colors have to be compatible, the adjacent colors. So we have to put red beside red. So if we have red on the right side here, the tile to the right must have red on the left. And up and down as well, we see blue, blue, or green, green, blue, blue, red, red, and so forth. Yeah. Okay, so this problem is undecidable. So we have this input set of dominoes like D. We can copy each piece as many times as we want to create an infinite tiling, and then the output should be true if there exists a valid infinite tiling, or false otherwise. Yeah. So what I'm going to cover today is we're going to start with the reduction and show that we can solve the domino tiling problem using OWL. And what that will imply for us is that given that this is undecidable, what could we say about OWL entailment? We could say that OWL entailment is undecidable too. Yeah, because if OWL entailment were decidable, and we could reduce this to OWL entailment, then OWL entailment would be, our domino tiling problem would be decidable, and that's a contradiction. Okay? So this is not my proof, this is based on Uli Sattler and various people have shown these proofs before for different flavors of OWL. So does D have an infinite tiling is the problem we have here, and the question here is, does one ontology in OWL entail another or not? So how can we encode a domino tiling question into OWL, an OWL entailment question is what we're going to start with. So we're going to show that we can model this problem precisely in OWL, exactly, and that's a problem. Yeah. So for reference, I'll go through these later one by one as we proceed, but I'll use some description logic, but I'll also use some turtle examples, so it's similar to what you've seen in the lab. Okay, so the first thing we're going to have to do is somehow define this in OWL. Yeah, it's not too hard. There's a couple of tricky parts, but we'll have to start with defining somehow what these pieces are and what dominoes are and so forth. So we're going to call here a tile. Sometimes they're called wine tiles based on the person who studied a lot this problem. We're going to define a tile as a piece, as a physical thing that we can pick up and put down somewhere in the grid. Yeah. So we have this set of tiles, or we'll call it a class of tiles later, which represents all of the pieces we can have. And we're going to say that a domino is a group of tiles of the same color, a set of tiles of the same color, or a subclass of tiles of the same color. So we see this is a domino here that represents the ones with blue at the top, red at the bottom, red at the right, and green at the left. Yep. So dominoes is a sort of class of tiles of the same color. So each tile must have a domino type. This is the first thing we're going to define in OWL in order to represent this problem in OWL and use OWL entailment to solve it. Yep. So each tile must have a domino type. So what does that mean? It means basically that we need to define this sort of thing here where we have a class of tiles and then we have subclasses of dominoes. Yeah. In this case, yeah, okay, so here we see still that we're just going to say that there's some subclasses. We're not going to say that they're disjoint and so forth. So we're going to define tiles as a class T, that's this whole thing here. And then we're going to define it as a union of all the classes of dominoes. Yeah, so the tiles is somehow the union of all the different dominoes we have. Yeah. So here we have the definition in description logics, and here we have the definition in term. Yeah. So in description logics, we say T is equivalent to the class of things of the union of D1, D2, dk minus 1, dk. What are D? All the D's are the dominoes. Yeah, all the different colors we can have. So we're saying that the union of all these is equivalent to the set of tiles. Yeah. So essentially what it tells us is that we can't have a tile in a domino outside the orange part here. Yeah. So this is the way we define the tiles and the dominoes. So this is our kind of initial definition. Yeah. So we have T is equivalent to the union of all of these D's. Yeah? So the D's are the gray things, the T is the orange thing here. What else do we need to encode? Well, the very first thing we should encode is we should say that actually we can't have a tile in two different dominoes. We should only have one tile, or each tile should only be in one domino. So we don't have this sort of situation here. Yep. So how we do this, we want to say that each tile can only be one domino type. Yeah. Any ideas on how we could say that in L? So we had the union, and we saw another feature which was very similar to union of. Not intersection, no. It was a variant of union. Disjoint union of. Yeah. So disjoint union of. So that tells us that it must be exactly one of these things. Yeah. So how can we encode this in L? We can encode this as a disjoint union. Yeah. So we define the dominoes as pairwise disjoint. So in what we'd have to do in description logics is say that the intersection of DI and DJ of each pair of dominoes is a subset of the empty set or the empty class. Yeah. And this for every pair IJ such that I is not equal to J. Yeah. Or I is less than J. So in Turtle, as we saw in the L class, we have a much more succinct way to do this, and we can define T to be equivalent to the disjoint union of D1 to DJ, all of the, or DK, all of the dominoes. Yeah. So this actually covers 1 and 2. So in one definition, we can cover each tile must have a domino type, and each tile can only be one domino type with a disjoint union of definition. Okay, so now we've set up somehow our tiles or dominoes. We know that each tile must correspond to one domino. We know that all tiles must have a domino. So we have this sort of situation here. We can't have tiles outside. We can't have tiles in multiple dominoes. We can't have a tile in here that's not a domino. So we're good, yeah, for this part. What's the next thing we need to define for the tiling problem? The tiling. Yeah. So what's the first thing we need to define about the tiling? What does a tile have? What does every tile have? It has a tile, so it has colors. So we'll come to that. Colors will be tricky. We'll come to that a little bit later. But just in terms of the structure of the tiling, a tile has a tile above and a tile to the right. Yeah. We don't really care about the left and the bottom because that's the corner tile in the bottom left doesn't have that, so it's sufficient to say a tile has a tile above and a tile to the right. So we're going to define that each tile must have a tile to the right and a tile above. Yeah, so we're going to create this sort of structure here where we say that each tile has a tile to the right and must have a tile above. So as you see, the colors are not right here because we still haven't covered, we haven't represented colors yet. So how do we define that a tile must have a tile to the right and a tile above? What kind of feature of L do you think we could use? You've seen? So it's like there exists a tile above and there exists a tile to the right. Yeah, min qualified cardinality we could use, yeah. And there's another version, so that would be each tile has min qualified cardinality 1 on property above from class tile. Yeah, that would work. There's a shorter way of writing that using another feature, which is some values from. Yeah, some values from. So we'll use some values from here, but min qualified cardinality, we could do something equivalent. So how can we encode this in L? Using some existential thing like min qualified cardinality or min cardinality or some values from. We want to define that a tile has some values from tile for right and above. So how does this look in description logics? It says that the class of tiles is a subclass of those that for which there exists for the property right. I use or here for right. an instance from the class tile, and there exists for above A an instance from the class tile. Yeah, or how you would see it as we would have seen it in the lab. We would use this here. Yeah. So we would say a tile is a subclass of the intersection of, because we want to say two things. We want to say the right thing and the above thing. So the intersection of some values from T on property or. So it says that every tile must have a value from T, an instance of a tile on property or, which I use or just for succinctness here for right. And must have some value from a tile on property above. So that captures intuitively precisely what we're showing here, which is that a tile has some values from right or above, or that each tile must have a tile to the right and a tile to the right and a tile above. Are we there yet? No. What are we missing from this? So with the left one, if we define the left one, in this case, we'd have a problem with the bottom corner tile. It is somehow equivalent. We could do that, but it's sufficient because right implies left. If we define the inverse, then it gives us somehow that information. Yeah. So it's a little bit neater just to work with right and above. Yeah. So what is problematic for the tiling here that we see? You can see the colors. They don't match. Yeah, they don't match. Yeah, so we have to define the colors. Yeah. So we could define the colors. We could define that every tile has a color above, a color below, a color to the right, a color to the left, and then say, do some matching. But we can just be a little bit cheaty here, not really cheating, but what we're going to do is we're going to define that the tiles to the right and tiles above must match the color of the current tile. Yeah. We're going to cheat a little bit. How can we encode this in Aldo? We could work on modeling the colors and doing that, and we'd probably get there. We're going to cheat a little bit, and we're going to define this mess of things here. So what are we saying in description logics here? We're saying tile D1. Let's say it has red at the top and blue at the right. Red at the top. I wonder, is there a better way? We could say red to the right because it's or and it's A. What's a color starting with A? I don't know. We could say black because it's close to A. Okay, red to the right and black above. So okay, so we have this domino D1, and let's say this domino, it has some particular colors. It has some colors, it has some color on the right line and it has some color on the above line, which we care about for now. So we say that basically we say that for the property right, it must have which in this case it has red. We define all of the dominoes here, the union of all the dominoes that have red on the left. Yeah, so if it has red on the right, then we just say, okay, then it must have a value from one of the dominoes that has red on the left. Yeah, and we just enumerate all of these. Yeah, so this is equivalent. And also for the above, then we must define that all of the values for above for this domino must have dominoes that have black at the bottom. Yeah. So we can enumerate all of these. This is not a problem because we have a finite set of dominoes. So this will be a bit messy, but we can define this given the example we've been provided. What about decay? So we do this then for every domino. Yeah, we do this for every domino. We say, what are the dominoes we can have above and what are the dominoes we can have to the right? Yeah. It gets a little bit long and messy, but it's finite. Yeah, it's at some stage will be done. It will be quadratic, this definition and the size of dominoes. So how does this look in turtle? As you can see, it's a bit of a mess, but it's perfectly reasonable. I mean, we can write it down. So we say that for each domino, Dn, we say it's equivalent to the intersection of all of those dominoes that have, okay, it is the intersection of the tiles that are compatible with it. So it has these values on above and the union of all the things that are compatible with it on the right to the right. Yeah. So we just say basically the tiles above this domino must come from one of the compatible dominoes for the above thing, and the thing to the right must have a compatible domino for the kernel. Okay, so here we cheat a bit and we say here somehow we'll have to take the dominoes and we'll have to figure out which ones are compatible and we'll have to define them in these restrictions here. So what we have now is essentially this nice matching thing. Yeah, so we have red to the red, blue to blue, and so forth. Yeah. Any questions so far? Okay. So what are we missing? I have a question for you. Are we there yet? And I just give a hint, we're not there yet. There's something else about the structure of the tiling we've not defined yet. So, and maybe there's a trick here that's maybe hiding it in the natural language. We say each tile must have a tile to the right and above. It's not saying that it must have exactly one, right? And in the structure, we assume it has exactly one. So we're kind of saying at least one tile, right? And we don't want it to have 2 or 3 tiles. So what we're currently allowing, although they have to be compatible, is this sort of situation here, where we have multiple tiles. Yeah, so we have we have different tiles are right and different tiles above. So what we'd like to then make sure and say is basically that these match to form a tiling. Yeah. So we want to say that these tiles here match. So how do we do this? We say we need to define that the tile right then above is equal to the tile above then right. Yeah. So we need to say that if you come from this tile here and you go above and right, then if you come from this tile here and go right and then above, you should get the same tile. They're the same. Any ideas how we do that? In L? So in this case, we need to use property axioms. So what is this thing about the tile above and right? How could we capture that? It's similar to the uncle example, right? Property chain. Yeah, so we can define a property chain above followed by right. And we can define a property chain right followed by above. And what do we say about both of them? So we would say, we wouldn't say directly same as, but we would say those chains are functional. If you remember, you can have one biological father or something like that. So now you say you can only have one of these values. Yeah. So we're going to define new properties. That would be the property chain of above right or right above. And then we're going to say that that property is functional. You can only have one of those things. Yeah. So we're going to define a diagonal tile, which is essentially either above right or right and above. And then we're going to declare the diagonal tile relation to be functional. So how does this work? In description logics, it looks like this. This is the composition symbol in description logics for property chains. So effectively A followed by OR is a subset of D, subproperty of D, sorry. And then OR followed by A is a subproperty of D, which is the diagonal tile. So this is above followed by right is a subproperty of diagonal. Property chain of OR followed by A is a subproperty of diagonal. And diagonal is function, which means that like a function, if you put in one value, you sort of expect one output, which could be a set, right? But you expect one output. It's deterministic. So what does this look like in L? We define our property chain axiom, diagonal, property chain axiom A followed by OR, diagonal L property chain axiom OR followed by A. Diagonal is a functional property, and that tells us essentially that now we can only have one tile in that position, diagonally above. So now we rule out this other case. Yeah. So are we there yet? Seems like we're pretty close, right? So there is one last case, and there's also some branching cases we've not considered, but we don't really mind too much, because if we have branching cases, by which I mean maybe we have multiple possible tiles here. However, there is one case that we need to think about, which is cyclic models. So it means that we could solve, essentially, we could have a tiling that basically allows us to have the same thing above it and right. Yeah. So we could have, for example, just this very simple example of everything is red. And then we could define that, I'm not sure if that's, yeah, maybe. So then we could define essentially that this is above and this is right. and it satisfies everything we've seen so far. Yeah. So this sort of tiling would actually satisfy. And then the question is, do we need to do something about this case? What do you think? If we had this sort of tiling, would it tell us that there is an infinite tiling? So do we actually need to rule out this case? We could rule out this case, yeah. We could say that above and right must be irreflexive. That would rule out particularly this case. Above is irreflexive, right is irreflexive, diagonal is irreflexive, which means that a tile cannot have itself as a diagonal tile. It cannot have itself above, cannot have itself below. We would need to copy the tile then. So this is, it would be important to note that this is really the same piece. Yeah. This is not, I'm not saying, that we can't have different pieces from the same domino. I'm saying that what we allow currently is that the exact same piece, the exact same part. We could currently, with what we've defined, allow this sort of situation that the same tile is above itself, or it's to the right of itself. Yeah. So we could remove this. We could define this to be irreflexive. We could define it to be asymmetric. If you remember the asymmetric, if we have A, B, then we can't have B, A. So for example, if father of is asymmetric, it means that A father of B implies that we can never have B father of A. Yeah. So we could define all of these things, but actually it's sort of not necessary because these sorts of tilings here, they witness or they tell us that there must exist an infinite tiling. So we just have to sort of unfold these cycles and we get an infinite tiling. So we could remove these things by defining a subproperty of right above to be transitive and asymmetric. So we say that somehow we can never have something transitively above itself or to the right of itself, but that's not necessary. Why is it not necessary? Because if we have a case like this, then it means that there must be an infinite tiling. Yeah, we'd have to prove that, but let's not get into those details. So if we weren't sure, we didn't know how to prove it, we could just use a few more OWL features to define that. Yeah. The nice thing about not using extra OWL features like asymmetry and transitivity, we'll see a little bit later, but the fewer OWL features we use, the stronger our proof. Yeah, because it says that with only these features, we can represent an undecidable problem. Yeah, which tells us that with only these features, we're already undecidable. If we use unnecessary features, it's a little bit weaker. Yeah. So the fewer features we use, the better. So are we there yet? Yes, we're done. We have represented the domino tiling problem with OWL. Yeah. So we've defined a set of axioms that basically models the domino tiling problem. A set of OWL axioms and class definitions for this. There's one last thing to look at before we complete the proof, which is what is the entailment question? Yeah. So what do we have our definitions, and then what do we do with them? We have our ontology now that describes the tiling problem. We have to ask a question. We have to set a problem, right? So the problem in this case, we need to figure out. So essentially, we have all of the things we just defined. We have modeled our domino tiling problem. And if we want to have an entailment problem, we have to ask, does something entail something else? Yeah. So the question then is, what should we put in this ontology here? So we're going to take this ontology O as what we just defined, and then we need to define some sort of O prime and ask, does O entail O prime? Yeah. Any ideas, maybe? Not so easy. So what we want to know here is if there can possibly be a tile. Yeah, because if there's one tile, if there is an instance of these classes if there's an instance of tile, it must be in a domino. It must have a tile right and above, and that tile must have a tile right and above, and so forth. So if there exists one tile, if tile is not empty as a class, there's two possibilities. Tile is empty as a class, which even if there is or is not an infinite tiling, everything's okay. But if there exists a tile, there must exist an infinite tiling, because we've just defined that the tile must have a tile right and above, it must be compatible, it must be the same on the diagonal and so forth. So the question we have to ask of this model we've created here, of our domino tiling instance, domino tiling problem instance, is whether or not there can exist a tile. So what should we put in O? We can put in O, for example, that the tile is empty, the set of tiles is empty. Yeah. If we can entail that the set of tiles is empty, it means that there is no infinite tiling. Yeah. If we know for sure that T must be empty, it means that there's no possible model where there is a tile, which means that there's no infinite tile. So this is sufficient. And now we've asked the question of a question equivalent to whether or not there is an infinite tiling here or not. We could also use satisfiability, which means we want to check if an ontology is consistent or not. So how we would do it with satisfiability is we just add that T has some member, X, doesn't matter what we put. So we say tile is not an empty class, and then we see, is that a contradiction? Yeah. So when would it be a contradiction? It would be a contradiction if all these definitions here for tiling state that basically this can never happen. We can never create this infinite tiling for the tiles. Yeah. So ontology O is satisfiable if and only if D has an infinite tiling. Otherwise, we can never instantiate a tile, because the second we have an instance of a tile, it must have the tiles right and above, diagonal tiles must be the same, the colors must be compatible, and we would have to create an infinite tiling for that to be satisfied. Any questions or doubts about that? Okay, so what do we learn? We learn, if you've seen the halting problem before, we know that we can represent the halting problem in terms of a domino tiling problem. I didn't show the proof for that, but I actually don't even know the details of that. But so we know that the domino tiling problem is undecidable, and then we can represent the domino tiling problem as an instance of an owl entailment problem. So what does it mean? It means that we could fairly directly as well, if we wanted to, we could remove this and we could just reduce from the halting problem to an ontology problem. Yeah, to an owl entailment problem. So what is the practical consequence of this? Owl entailment is undecidable. Yeah. Great. Okay. So I think a key message here is we spoke about the specific case of owl, but this applies very quickly to knowledge representation languages. So if you had this idea of using some sort of logical language to write down everything you know, and then you create these rules or this sort of semantics or some sort of definition so that machines could then take what you know and infer new things, very quickly you run into this decidability issue. Yeah, so computers are limited, machines are limited in what they can reason about in terms of telling us about the world. Yeah. So not just is owl undecidable, but basically in knowledge representation, this is a general issue. Yeah, that if you add too much power to your language in terms of what you can state, you can very quickly get into undecidability issues. Yeah. So there's limits to what machines can reason about and tell us about the world. If we tell them everything and we give them a very powerful language to reason about, then reasoning becomes undecidable. So, okay, what are we supposed to do now? So we have this language, we have this owl language, and this is a real, problem people faced. Yeah, you have a knowledge representation language. The full language is undecidable. Yeah, so which means that basically, if we give it an ontology, it may never finish sometimes. Yeah. So what do we do now? And there's basically three main answers to this. So what's the first possibility? I'll give you the first possibility. It would be, I don't care. I keep my full language. I have my reasoner. It will take all ontologies. If it finishes, it finishes. If it doesn't, that's life. That would be the first option. Perfectly reasonable option. Yeah. What would a second option be? Any ideas?
Try to fix that.
Trying to fix it, okay, yeah, and that branches into two. So what you're saying is to fix it, it's the run forever part. Yeah, so how do we fix the run forever part?
Limit the number of rules.
Yeah, so you limit somehow what you can say. So you say, okay, I'm limiting somehow the inputs. Yeah, I'm not allowing these inputs because I'm not sure if they'll finish or run forever. Yeah. So in this case, rather than limit, let's say, the number of rules, what you can do is limit the language in the owl sense. You can say, let's turn some features off. Let's start turning off some features until we know we're decidable. Yeah. Another option. So what we want then with the other option is we don't want to limit the language. We don't want to limit decidability. We want decidability. We don't want to limit the language. There's only one thing left we can buy.
The answer might be wrong.
Exactly. Yeah. So we can say, okay, well, maybe what we'll accept then is that the answer might be wrong. Yeah. So we have these three options. Yeah, we can either kind of trade decidability, we can trade the language, or we can trade the correctness of the answer. Yeah. So we can accept in the third case, we can say we use the full language. We have this algorithm that we know will finish, but it might in some cases deliver the incorrect answer. The most common would be to say that this is not entailed when it actually is. Yeah, because you can't find a way easily to entail something. Yeah. So these are the three. Yeah. So we have accepts any ontology in the AL case, so it accepts any input. We have the always holds, always, or our algorithm will always finish, and the response is always correct. And we have to choose two of these things. Yeah, we can't have all three. Okay. So the three options then in the different intersections, if we try to at least take two things, we can have incomplete reasoners. So often by that I mean the most common case for the incorrect answer is that it says it's not entailed when it is. Yeah. So we can have incomplete reasoners that halt. So we have a complete language, all of vowel, might sometimes miss some inferences or some entailments, but it will always finish. And this is the type of reasoner you've used in the lab. Yeah. So if you use certain features of vowel, you wouldn't get the inferences you're expecting. Yeah. We can have complete reasoners that may not halt. So this is essentially, we just accept that, okay, sometimes this algorithm is never going to finish. We take any AL ontology and we do our best to do reasoning with it. Yeah. And the third option again is restrict AL so reasoning becomes decidable. So we restrict somehow what ontologies we allow to ensure that it will always halt with the correct answer. Yeah, but we won't be able to say everything we might like to do. So we'll talk a little bit in brief about these three options, and that's kind of the core of the class. And I'll talk a little bit about an algorithm for different algorithms for this. And that will be the end. So we'll talk a little bit as well about like how the reasoner we see in the lab is working, what kinds of techniques they're using. And we'll see a new reasoner on Wednesday. That is the third type. So we've worked with the first type, and we'll work with the third type on Wednesday, which will allow us to do more complex forms of reasoning. Incomplete reasoners that halt. So in the labs, what you've been working on is basically given some data. You need to create an ontology or some AL definitions that you send into this reasoner in the background of RDF Playground, and then it creates some entailments for you. Yeah, and then you check to make sure the entailments you expect were given. So what is this reasoner actually doing? So what it's doing essentially is incomplete materialization using rules. So it's using a rule-based reasoner, also data log, logic programming kind of reasoning. So it's applying rules. So we'll talk about those rules. So we saw rules for RDFS when we spoke about RDFS. We also need to cover some of AL. So the idea basically is just to extend these rules to cover a bunch of AL stuff as well. Yeah. And we're going to apply those recursively until we can't find anything new, and then we return that as the results of the reasoning. So there's this language, this standard called AL2 ORL, which is AL2 rule language, essentially, which tells people if you're okay with missing inferences, sometimes if you just want to get a bunch of inferences, then go ahead and use this profile. Yeah. So what is it doing? It is in the lab, what we're using is RDFS in the lab 3, yeah. And since then, we've been using the AL2 ORL RDF rules. So we've been using a rule-based reasoning. So let's see some of the rules briefly. I'm not going to go into all of them. There's about 80 of them. I had to implement these for my PhD at some stage. It was a lot of fun. And so let's take some examples, and you'll have the rest for reference on the slides. We have this rule ID here called rep S, equality replacement S, and we have S same as S prime, SPO. Any ideas what we might get out here?
S prime PO.
Yeah, exactly, S prime PO. So this talks about the replacement of S. If they're the same as, we can replace the S. We have another one for P and O that's the same. Here we have X same as Y different from Y. X same as Y, X different from Y. So that would be a contradiction, right? A false. Yeah, so X cannot be the same as Y and different from Y at the same time. Okay, so there's more rules, but you can go through them in your own time. We'll just pick some just to give it examples. P is a functional property, XPY1, XPY2. Y1 same as Y2. Yep. We have transitive property, P a transitive property, XPY, YPZ. XPZ. Yeah. We have P1 inverse of P2, XP1Y. YP2X. Yeah. And here we see the dual, right? So if YP2X, then XP1Y, because it works in both directions with inverse. Yeah. So very good. Again, there's more rules you can kind of check through a little bit later. We have the most complex ones here, which are the classes. Well, okay. So we have C is an intersection of C1 to Cn, C1, C2, C3 up to Cn. Y is an instance of C1 up to Cn, C1, C2, C3, Cn. So what could we infer about Y? So we have, for example, DCC professor is an intersection of professor and DCC staff. If someone is professor and DCC staff, they must be DCC professor. So what we infer here is that Y is a C. Yeah, it's the intersection. Y is C. We have union. We have C union of C1 to Cn. Y a Ci, some C between C1 and Cn. What could we infer about what could we infer about Y? So we have DCC staff instance of union of DCC professor, DCC functionary. I don't know how to pronounce it. There's no translation for that. DCC administrative staff, DCC professor, or DCC academic staff. So if we know then that someone is a DCC administrative staff, we know that they must be DCC staff. Yeah, so they must be in the union. So YSC. Yeah. Okay, so and the difference between intersection is it has to be an instance of all of these things, and in union it suffices if it's in one of those things. Yeah. What about this one? We have all values from. We have X all values from Y on property P, UPV, UAX. Right. So let's try to exemplify this. Binary star all values from binary star on property sibling. No, I'll use one where they're two different things. Planet all values from moon on property orbited by. Earth a planet. Earth orbited by Luna. Earth a planet. So what could we infer? We know all the things that orbit planets are moons. We know that the moon orbits Luna orbits Earth. We know that Luna is a moon. So yeah, sorry, we know that Luna is a moon. Yeah. I should have picked a different moon and planet, but okay. So we have rules standard for has value, max cardinality, some values from, and so forth. Okay. We have schema level rules. We have if C1 subclass of C2 and C2 subclass of C3. We have C1 subclass of C3, transitivity of subclass. C1 subclass of C2, C2 subclass of C1. Yep, equivalent class in this case. It wouldn't be al same as, but it would be equivalent class because we can only replace them when they're the type of something. Yeah, so we can't replace them in other places. But when they're the type of something, we can replace them. So we'd have C1 equivalent class C2. And then we have P domain C1, C1 subclass of C2. P domain of C2. Exactly. Yeah, P domain of C2. Yep. So these are all in the rule set. So we also get not only rules to infer like new facts in our vocabulary, but we can also infer new RDFS and OWL axioms as well. Yeah. However, the whole point with L2 or L or DF, like we discussed, is that it's not a complete set. We could continue defining new rules ad infinitum. We could continue adding more and more and more rules that are correct, and we would never finish. Yeah, we have an infinite number of rules we could consider. So here's some stuff that's missing. We have P, a reflexive property, X, a thing. So a reflexive property is something where it holds to every individual itself. Yeah, so similar to. We could say similar to is a reflexive thing, a reflexive property because everything is similar to itself. Yeah. So in this case, if we say P, a reflexive property, and X, a thing, we can say XPX. Yeah, so X is something, P is a reflexive property, then we must have X is related to itself by P. X has self-true on property P, U X. So the classic example here is narcissist has self-true on property loves. Aiden, a narcissist. So we would have Aiden loves Aiden. Yeah, or U. X has self-true on property P. So we have the same thing. Narcissist has self-true on property loves. Aiden loves Aiden. Aiden, a narcissist. Yeah, UAX. X inverse of X. Okay, so these are more instance level things. Here we have some things that infer axioms. So if we say X is the inverse of X, what could we say about X? So there's another way to say this, which is that X is a symmetric property. Yeah. So if sibling is the inverse of sibling, then that's the same as saying sibling is a symmetric property. Yeah. X inverse of Y, Y inverse of Z, or Z. X inverse of Y, Y inverse of Z. I have to think about this one. Yeah, okay. What do you think? It's a fun one. The same. Which ones? Yeah. Yeah, exactly. Yeah. So X and Z in this case would be equivalent properties. Yeah, very good. We have X inverse of Y, Y a functional property. This one's maybe not so interesting, but okay, it's more syntactic. X inverse functional property. Yeah. X complement of Y and Z, then we can infer that X is disjoint with sorry, not that. Which is true as well, but okay. So if we say X is the complement of Y and X is the complement of Z, what can we say about Y and Z? So what is complement of? It means everything that's not X. Yeah, so Y is everything that's not X, and Z or Z is everything that's not X. So what does it mean about Y and Z? It's the same. Yeah, so we have equivalent class between them. Yeah, because they're both everything that's not X. Yeah, so they're sort of like a set of everything, and then everything that's not X and everything is not X, it must be equivalent.
But Y and Z can be complement each other.
No, because when you say complement of, you create a dichotomy where everything is either X or not X. Yeah. So the classic one is sort of dead and alive or complements of each other. Yeah. So something is either one or the other. It's like a disjoint union over the set of everything. So there must be a code. Okay, so this is all of the rules are here. We saw all of the rules. There's maybe some syntactic stuff I left out, but you can check them out in the website in the W3C recommendation. So this is a web standard effectively that was published in 2012. Any questions or doubts about that? So we have these rules, we just apply them until we don't find anything new, and then we stop. That's what your reasoner has been doing in the labs. How is it incomplete? In what cases do we not get what we expected? So the first case is this sort of example here, which is disjoint union of. We have Vincent is a type person, yeah? And we know that person is equivalent to the disjoint union of criminal and lawful, which means that every person is either law-abiding, is either a criminal or follows the law. So we say Vincent is a person equivalent disjoint union of criminal and lawful. So what should we be able to handle here? We should have somehow this knowledge that Vincent is either criminal or lawful. We don't have a very concrete inference here, but we do have knowledge that he must be one of these two things. Yeah. So if we add some more information and we say Vincent is a person and a godfather, person is equivalent to what we saw, disjoint union of criminal and lawful, godfather is disjoint with lawful. So if you're a godfather, you can't be lawful. What do we know now? What should we infer? So we know since Vincent is a person, there's two options. He's either criminal or lawful. We know he's a godfather. A godfather can't be lawful. So we should know for sure that if Vincent is criminal. Yeah. So we rule out one of the possibilities. So this is called disjunction. It's where we create multiple possibilities. And we don't know exactly what is the case, but we need to explore those different possibilities to see if something is entailed or not. So L2 or L rules will completely miss this. It won't even get close to this because it doesn't consider this sort of disjunction, like considering multiple possibilities to see if something holds or not amongst these possibilities. The other thing that L2 or L does not do is it cannot handle negation. So it can sort of pretend to handle negation. For example, if we have X complement of Y, well, actually, it doesn't even tell you that. It can do things with disjoint with, but it only handles negation as if it were positive statements. So if you say something is not true, it can apply some rules and generate something based on that, but it doesn't really understand no. It doesn't understand the logical negation. Yeah? So it also misses the information that Vincent is not lawful here. It won't understand that. It can on a syntactic level, it can handle a negation, but not the full semantics of what it means. Okay, so we had this example as well from the first class on now. It seems like a long time ago, actually, but I guess it was. There was also 2 weeks we had in between. So the Sun Valley trunk case. So we say that parent is equivalent to has child person. And then if we say that Michael is a parent, then we know that there exists a child that Michael has that is a person. Yeah. So we're going to extend this a little bit, and we're going to say Michael is a biological parent. Biological parent is equivalent to the following class. The class that have some values from person on property has biological child, and has biological child is in the domain fertile. Somebody who can have a child. Yeah. So what should we be able to infer here? So Michael is a biological parent. Biological parent is equivalent to the class of things that have a person and has biological child. That means that Michael must have some biological child. Yeah. And then it says that has biological child domain fertile, which means that the subject of anything that has a biological child must be fertile. So it must mean that Michael is fertile. Basically, Michael is able to reproduce. So Michael type fertile. So L2 or L will miss this valid inference because it misses the information that Michael has some child. It doesn't write down that Michael has some child, and for that reason it won't get this inference. So it's not good at handling existentials. Yeah, these things that exist, but we don't know what they are. Yes, Michael has some child here, we don't know what it is, but that must infer that Michael is fertile. I'm proudly awarding this example the worst example of the course. Very proud of how terrible this example is, but okay. I think at one stage I wanted to change it, but I use it later in the slides and it just requires too much effort. So I just decided I would give it the worst example of the course. So how is L2 or L RDF incomplete? So we have missing features, things that are just, there's no rules for these, like reflexive property, has self-mint cardinality and so forth. We have problems with the disjunction where we have multiple possibilities that we need to explore. We have problems with existentials where there exists something, but we can't write it down. We don't know what it is. We can use a blank note maybe, but then the problem with creating blank notes is when do we stop? We can easily start to create infinite blank notes. Yeah. Problems with counting. This is very complex. So rule-based languages are not very good at these sort of counting things. Problems with negation. So we don't really understand no. We can do some syntactic stuff with negation, but there's no real idea of negation in the language, in the rule language, in the rules. And incomplete schema inferences, which means that we're never going to get all of the OWL axioms we'd like. However, we still get a good chunk of interesting, as you've seen in the labs, somehow interesting and relevant inferences. And the really nice thing about L2 or L is that it will work for any ontology. So it's considered to be very nice for web data, where people could have a mix of all sorts of different ontological features. And we can apply these rules and at least get some interesting inferences out, even if we don't know if we've gotten everything. Yeah. So in terms of the entailment, just to briefly mention, when we do materialization, it's sort of producing all the things that we're saying yes for entailment. Yeah. So in some cases, we're saying no by not including it in the entailments, and that's not completely correct, right? It means essentially that it's incomplete, or in some cases, we're saying no to entailment when we should be saying yes. Our zip rates. So how can we intuitively conclude about, what can we intuitively conclude about Zia here? We've already spoken about this. We can say that Zia is a saproid, and we give a bunch of definitions, but we would not get this entailment with L2 or L or DF. However, with the reasoner we're going to see on Wednesday, we can get this sort of entailment. Yes, we're going to use a more powerful reasoner in some sense that can address some of this. Okay, so that's the first option. Just apply some rules, get some inferences. We might miss stuff. That's life. Any questions about that? Okay, the second type is complete reasoners that may not halt. This is going to be a very short section of the course because there's only one proposal I've seen of such a reasoner, which basically uses a first order automated theorem proving tool to implement reasoning for all of L, which is called L2 full. It's basically everything, anything you could say in turtle using L. Is L2 full. So they use first order automated theorem prover. So essentially the idea is you translate this to first order logic, and then you use some first order logic systems and engines to reason over it. In some cases it will never terminate, but that's life. So that's about the only work I know, which I think is a pity because I think it's an interesting alternative as well. So what's the downside of this? Reasoner may never halt. That sucks. Okay. What might the pros be in this case? We avoid complicated decidability restrictions, which is what we're going to see in the third option. Yeah. So the third option, when we look at it, we're going to be looking at how to restrict the language to be decidable, and we're going to try to keep as much as possible. So what the motivation behind the third option is basically that we really always want reasoning to be decidable. We really always want the reasoner to return a correct answer. So we want the answer to be correct, and we want the algorithm to finish. Yeah. So this turns out to be not so easy to do. Yeah. So we can't like have some sort of dichotomy with that. So we can't say precisely where the boundary of decidability is. And also the restrictions can be a little bit messy. So imagine you were creating a programming language back in the old days, let's say the 50s, 60s, 70s, whatever. And you decided that you wanted to make your programming language always decidable. So decidable in the sense that's kind of not the correct term, but that whatever program somebody wrote, it would always finish. Yeah. So what would you do? So your first option would be to remove all loops and recursion, for example. Yeah. Remove all loops, all recursion. Would that be a good idea? No, because your programming language would then be very limited, right? So your programming language would be very limited to if it had no loops or recursion, right? So what might you start to do? You might say, oh, in this case, if it's like for I in 1 to 10 or something like this, if it's a sort of a finite loop, you could say, okay, this is guaranteed to halt. So you can start to syntactically restrict certain loops, and you can start to get into more details. But the more fine-grained you get, the more types of programs you allow and will be decidable, but the more complicated the language will be. Yeah. So defining kind of these restrictions at a language level is kind of a bit complicated. So the other option is, as per this reason, don't restrict anything. Sometimes the program won't hold. That's life. Yeah. So the third option then goes into this idea that we're going to restrict OWL to ensure decidability. This is a pretty controversial topic in the semantic web. So people really dislike this, researchers. Some researchers really dislike this direction for knowledge representation. Others think it's necessary. Others think it's interesting as an idea to explore, but it's quite a controversial topic. So we've seen how to prove that something is undecidable, and the idea now is that we're going to try to guarantee decidability. So how can we prove that something is decidable rather than undecidable? Any ideas?
There's that body than that one.
Yep. So by far the most common and most useful way of proving that is that you give an algorithm that holds, yeah, for the problem. There is another way, which is you can show that there exists an algorithm without giving details of the algorithm. So usually this is sort of like a brute force time space thing. Your whole problem space fits within this amount of whatever. Actually, it doesn't even matter for decidability. It's finite, and you could iterate over all of it and look at everything and then do that. Yeah, without actually describing I guess that is describing an algorithm. But yeah, so sometimes you can have non-constructive arguments that don't tell you the algorithm, but shows it's decided. So we want to give an algorithm that holds. So the description logic community is something, this description logic community has been around since before OWL was proposed in 2004, even before the predecessors of OWL were proposed. The main idea that they had was that they wanted to use first order logic, but the big problem with using first order logic is that it's undecidable. So you can't necessarily use a machine to reason within first order logic. You can, but sometimes it won't hold. So their big question is, okay, what do we turn off in first order logic to enable decidability? Yeah, so what things do we not use anymore? And then the first order logic community heard of the OWL work and they realized these two things are very similar. The other big difference with first order logic is they focus on binary relations, whereas first order logic doesn't. So binary relations like graph-like data. Okay, so this community realized that their theory could be useful in the design of the OWL language. So what we have now currently in the most recent version of OWL, OWL2, we have OWL2 full, which is the unrestricted, undecidable language. We have OWL2DL, which is sort of the maximal known restricted decidable version. It's sort of like trying to keep as much as possible, but also guarantee decidability, provide an algorithm that will actually give you the correct answer, yes or no. And then we have certain flavors or profiles of OWL, and one of those is OWL2RL that we saw previously. So any ideas what we should restrict to make OWL decidable? So we have OWL2 full, like what you've been using, you didn't restrict anything, you were using OWL2 full completely openly in the labs. So what would we have to turn off in OWL2? In OWL, sorry, just OWL in general, I refer to OWL, OWL2, the newest version. What would we have to turn off to make it decidable? So if we look at our proof here that we had of undecidability, we know that we should never be able to write down this ontology and get this question. Yeah. If we can write down this ontology and express this entailment here, that's sufficient for whatever we use here is already undecidable. Yeah. It's already enough to do the undecidable proof. So what does that mean? It means that somehow we're going to have to turn off some features in here. Yeah. So what the OWL people decided to restrict in this case is functional properties should only be simple properties. So essentially they restricted this general class of things, which is counting on non-simple properties. Non-simple properties are transitive properties, they're chains, they're property chain axioms and so forth. The reason why is that there's some nice properties, which I'm not going to get into in too much detail. But when we have models that form trees that branch, it's quite okay. So, however, if we start to define functionality on chains or transitive properties, we can create these things that create graphs, like these graphs, these like grids that we saw in the case of the tiling, and that's a problem. Yeah. So this way of sort of like branching out, let's say, for example, a tree-based model would be something like we have a human who has parents that are human, who have parents that are human, and so forth. Yeah, that does not force somehow us to connect that this person in way back in the ancestry is the same as this person here. That sort of type of model creates lots of problems. Okay, in any case, so we're going to turn this off. We're going to turn off functional properties being used on complex roles or complex properties, for example, properties used in chains or transitivity and so forth. Is this enough to guarantee decidability? What we've done is we've turned off this last part here. So we can't define this thing to be functional. Yeah, we can't define that the diagonal thing is above right is the same as right above. Yeah. Are we done? Is our language now decidable? So we take OWL and we remove this this thing. Is it decidable? No. We've just removed one way to prove undecidability. It doesn't mean that there aren't other ways to prove undecidability, right? So what we need to do is go back to the general idea, which is we need to get a profile and give an algorithm for it and say this algorithm is complete for this. So is it enough to decide to guarantee decidability? No. Well, we don't know. Maybe it is, maybe it isn't, but we'd have to prove it. We just know that this undecidability proof won't work. There are many other proofs we could use that may not need this particular feature we turned off and use other features as well. So how do we guarantee decidability? Give a sound and complete algorithm, by which I mean it will always return. It will always give the correct answer. And it will work for within maybe this profile of the language. So L2DL restricts amongst the things that amongst some other syntactic stuff, but the main restrictions would be that functional properties must be simple, so no chains, no transitivity. Properties used with half-self cardinalities, inverse functionality, asymmetry, and irreflexivity must be simple. Yeah. And we need to follow specific RDF syntax and explicitly declare classes and properties and so forth. And there's a bunch of other stuff as well. Yeah, so it gives us a bunch of different restrictions. So it gets a bit messy. However, in L2DL, so long as we are both of our ontologies follow the restrictions that are defined, you are guaranteed a correct answer to an entailment question. So it will return yes only if they're entailed, and will return no only if they're not entailed. And there's no more question of is this supported by the reasoner or not. Everything within that restricted language will be supported completely by the reasoner. So we're good. Yeah, so in this case, we can get this sort of inference here, which is Vincent the person, the godfather. Person is either criminal or lawful. Godfather is not lawful. Therefore, Vincent is a criminal. So any ideas of how we could implement this? I'll give you a small flavor. Maybe any ideas? Has anyone seen anything like this before? How to implement something like this? Maybe you've seen or you've heard of the term in other settings. It maybe has certain relations, but it would be basically model checking. Yeah, so we have model theory, and we're going to check models of this possible sort of possibilities, possible worlds that could be described by these definitions. So the core idea is fairly straightforward. So the idea is we're going to use an algorithm called the Tableau algorithm, which somehow keeps track of what is true and what is false in different possible worlds that exist. So the idea is if we want to check the entailment O entails O prime, we're going to add not O prime to O, and I'm going to assume for simplicity O prime is just one axiom, one fact. Then we're going to expand knowledge using rules. So we're going to somehow try to expand, or we're going to generate a model of possible world that can exist. And we're going to try to expand out everything we know and expand out everything we know until we get to a point where we can't expand anymore. And then we're going to check meanwhile for any obvious contradictions. Yeah. Okay, so let's have a look at that. Oh, sorry. So the last part that's really important is if and only if every possible world, every branch is inconsistent, then O entails O prime. Yeah. So we're reducing from entailment to satisfiability in a way. Let's have a look at an example just to get a flavor of what's going on here. We have Vincent as a person, a godfather, godfather disjoint with lawful, person equivalent class disjoint of lawful and criminal, and Vincent is not a criminal. Yeah. Why do we have Vincent is not a criminal? What we're trying to prove is that Vincent is a criminal. So if we want to see if Vincent is a criminal is entailed, we negate it and we add it to our ontology. Yeah, we add it to O. So this is the negation of O prime that we've added to O. So now under disjunction, we need to expand all possibilities. So what are the possibilities here? We know that Vincent is a person, and we know that a person is either lawful or criminal, cannot be both. So we need to look at the possibility that Vincent is lawful or criminal. So we branch for or. Yeah, so we consider the case, okay, Vincent is a person, godfather, godfather disjoint with lawful. And instead of saying Vincent is an instance of this class, we say Vincent is directly lawful. We assume, let's say Vincent is lawful. Yeah. Vincent is not a criminal. So what do we see here? Do we see any contradiction? So we see Vincent is a godfather. Godfather disjoint with lawful. Vincent lawful. That's a problem, right? That's a contradiction. So based on this contradiction, okay, it means that this Vincent is not a criminal is now contradicting with this. Yeah, well, we didn't even need it in this case where we could just tell from the base relations. What about in the other case? So let's assume, before we assume that Vincent was lawful, now we're going to assume that Vincent is criminal and explore the other alternative. So we have Vincent the person, Vincent Godfather, Godfather disjoint with lawful, and now we add the other possibility. Vincent is a criminal and Vincent is not a criminal. Right? What do we get any contradiction here? In the last part, we say Vincent is a criminal and Vincent is not a criminal, which is a contradiction. Yeah. So it means that in this case as well, we have a contradiction. So if we negate O prime and add it to our ontology, it creates a contradiction under any possibility. What does that tell us? That O prime must be entailed from all. Yeah. Okay, so in this case, we knew this wasn't, without even adding this this part, we knew that it was already inconsistent. In this case, we needed the new fact to be negated, and that goes inconsistency. Yeah. So it's unsatisfiable in all branches, therefore O union not O prime is unsatisfiable, therefore O entails O prime. Yeah. So if negating what we want to entail and adding it to our ontology and then expanding out as much as possible all the information we have, if in all of these branches we find that it's inconsistent, we know that the thing is entailed. So this is kind of a bit of a tricky thing to maybe understand. So we'll look at the positive case or the negative case, let's say. So in this case, we have Vincent, so in this case, we're entailing Vincent as a criminal. Yeah, we get this entailment from this algorithm. Let's look at a case that isn't entailed. So Vincent type lawful, is this entailed from these same definitions here? No, there's nothing here to tell us that Vincent is lawful. We know that Vincent is a person, which makes him lawful or criminal. We know that he's a godfather. We know that a person is equivalent to this, okay? And then we know a godfather is disjoint with lawful, but there's no reason to believe here that Vincent is lawful. Yeah, there's nothing to entail that. So what happens with our algorithm if we try to see if this thing is entailed when it's not? So this time we add Vincent. So not Vincent type lawful, we negate what we want to check the entailment for. We add it to our ontology. We have some possibilities. We have the possibility that Vincent is lawful or Vincent is a criminal. So we branch for the different possibilities. In this case, we branch for the possibility that Vincent is lawful. And then we have Vincent not lawful. So we have a contradiction straight away, yeah, on this branch. So in this possibility, this does not hold. So that's fine. However, on the next branch where we check to see if Vincent is a criminal, here we add our fact Vincent is a criminal, we consider that possibility. Now we have Vincent is not lawful. Can anyone see a contradiction here? So we have Vincent a person, a godfather, godfather disjoint with lawful, Vincent a criminal, not Vincent type lawful. There's no contradiction here. So there's no contradiction here. And what does that tell us about the original entailment? It doesn't hold. It doesn't hold because it would be consistent here in this model. This is a possible model, yeah, where if Vincent were not lawful, this would still be consistent. There is a possible way in which Vincent could be lawful, yeah, or Vincent could be not lawful. Sorry. So if there's some possibility, if there's some possible world where Vincent could not be lawful and it's completely consistent, then it means we can't entail that Vincent is lawful. Yeah, it's kind of maybe tricky to understand, but hopefully you get the idea. So the main idea here, I guess, even more high level than reducing entailment to satisfiability, is the idea of just branching. For every possibility, we branch and we explore and we see if the thing holds or not in these different under these different possibilities. The same for so in this case, sorry, it is not entailed, and the tableau tells us that it's not entailed because there is a possible configuration of things in which Vincent can be not lawful, and that is consistent with one of the possible worlds or possible configurations that this ontology gives rise to. So returning to the worst example of the course, we have this example here, and we have existentials. So in the tableau algorithm, and this is rather more simple, the idea is if we know that something exists, what do? We create some X and we say, okay, there's this X thing here, something exists, and we assume it to be an individual. Yeah, so we create some sort of fresh individuals to represent these existentials. So in this case, we have Michael, a biological parent equivalent class of having people on the property has biological child, domain fertile. And then we want to see if this implies that Michael is fertile. So what do? We add the negation of what we want to entail to the ontology Michael is not fertile. Yeah. We want to see if this contradicts every possible world here. So what is the complicated part here? The complicated part here is that we have this definition which gives rise to existentials. Because Michael is a biological parent, we know that Michael must have a biological child that is a person. Yeah. So what does this mean? It means basically that we are going to need to postulate this X, this child. Michael has biological child X not referring to Twitter or anything like that. X type person. And then we fill out all of the details we know about X. And then that simplifies somehow what we need to check, which is if there's an inconsistency or not. Once we have that Michael has biological child X, and we know that has biological child is a domain of fertile, then we know that Michael must be fertile. And that simplifies checking for the inconsistency because we have Michael is fertile, Michael is not fertile, which means that it must be entailed. Yeah. So this is an inconsistency, and this tells us that we have the entailment we're looking for. So we have Michael is fertile. So we can get this sort of inference as well. We can get inference with counting, we can get inference with existentials, we can get inference with negation, we can get inference with all these things. One of the key points here as well, just to mention, is if you've heard of this logical principle that everything follows from a contradiction, this is the reason why. Because if you start with a contradiction, and if you use this unsatisfiability for entailment, then all of these branches will be unsatisfiable before we add anything. Okay, so this is the Tableau algorithm. And the key point here is that so long as O and O prime follow the L2 DL restrictions, we are guaranteed a correct answer to this entailment question. Yeah. So you can be assured that if it says yes, it's entailed. If it says no, it's not entailed. And as well, this algorithm will hold. Yeah. So this is the cool thing about these algorithms. However, it adds a lot of complexity to OWL, and people have argued, this is too complicated for the web, and our web developer is going to use this to add data and so forth. So there's some debates about this. So the Tableau algorithm is just brute force checking models of the ontologies. Optimizations and tricks beyond what I discussed are possible, which mainly say that, okay, if we're going down this branch and this branch creates these branches and these branches create these branches, that at some stage we don't need to expand beyond a certain level, because if we find an inconsistency, for example, we know that all the child branches must be inconsistent, and there's other various sorts of checks and ways to limit the search space of possibilities. Okay, so why do we need to restrict OWL in that case? Essentially, the idea is that we need to restrict OWL here because if we don't and we use this algorithm, if we just had full OWL, sometimes it would branch forever. It would start creating existentials, and it would create disjunctions and branch and branch and branch and consider a never-ending set of possible worlds. Yeah? The set of models that would need to be checked would be infinite. So, okay, we have a complete entailment algorithm that supports a lot of OWL features and terminates. So this is great news for us. Any questions about the Tableau? Maybe I know it's maybe a bit kind of tricky, difficult to understand at first. So the key idea is to essentially explore all possibilities, and in this way we can, if there's a limited number of possibilities, if we can restrict our language in a certain way, then we can be sure to check all possibilities to see if something holds or not. Okay, so cool thing is that with this example that we saw, we can actually now do this sort of reasoning using this Tableau algorithm, because we have enough information about existentials, disjunction, negation, and so forth to do this. Why is this example challenging for rules? It's challenging for rules because Zach is a zebroid, and we know zebroids have one zebra parent and one non-zebra equine parent. But we don't know which is which here, Marty or Leah. It creates two possibilities. Marty is the zebra or Leah is the zebra. Yeah. And with Tableau, we can consider both of those options that arise. Okay, so this is great. We have this, we have some restrictions on the language, which is not so nice, but okay. We have some restrictions on the language. We have an algorithm that terminates, that is decidable and is guaranteed to provide the correct answer. Can anyone see any potential problems I haven't discussed conceptually with this? So there's a few practical problems. The first is we have to give the entailments to check. So it's in the lab setting, we're not really giving the entailments to check. We're giving an ontology and we're saying, give me entailments. We're not saying, here's O prime, can you tell me if this follows or not from the ontology? There's some tricks to reduce from one to the other. Well, from materializing the entailments to entailment checking is easy. You write out all the entailments and you see if something is in there. But going the other way is not so easy. Yeah, you can sort of brute force with your vocabulary, create different facts and check them. Okay, but yeah, so there is this complication. Things can be done about this, but you cannot just ask to compute the entailments. The restrictions are complicated. Okay, they are very complicated in times and often are broken by real world ontologies. So what happens when an ontology doesn't conform? That's a big open question. Should you just remove that axiom, that definition? What should you do? Tableau entailment checks are really expensive in the worst case. Yeah. So if you branch every time there's an OR and there's multiple ORs, you can imagine that this creates an exponential number of possibilities. Yeah. So branch for every disjunction suggests exponential. And in fact, it's this in this complexity class you probably never heard of. N2 exp time complete. Have you heard of NP complete? So that's the N here. Have you heard of exp time, exponential time? So that's a broader class of problems that are all the NP problems would be in exp time, but there's other problems which are the problems that can be solved in exponential time. Have you heard of 2 exp time? No, these are the problems that are in the doubly exponential space. So these are the 2 to the 2 to the n. Yeah. So what this tells you is the n here says non-deterministic. We have a non-deterministic machine that's really lucky, can somehow magically guess things that are correct. Yeah. And then we have, if we have a non-deterministic machine, then it's doubly exponential. So this is like, O2 to the 2 to the n on a non-deterministic machine. So this is pretty bad. Yeah, so, and if we have a deterministic machine, well, we don't know, but one could assume that it would be 2 to the 2 to the 2 to the n. So yeah. This, however, is worst case. So it's worst case in the sense that many ontologies will work, but at some stage your ontology will just have this loading cycle going on forever and will take a long time to finish. Yeah, so the good news is that with all these complications, now we have decidability. So checking entailment is guaranteed to hold for L2 restricted ontologies. But given the cost and the amount of time it might take to reason about these ontologies, yeah, the entailment might not finish before the heat death of the universe. So if you could run it, you know it will stop, but you don't necessarily know if it's going to stop in a useful time. Yeah, it could continue until the heat death of the universe running. So this is one of the major arguments against this this drive or this focus on maintaining decidability. That why do you logically need or formally need to guarantee decidability if in practice you can't kind of guarantee that it will finish in a reasonable time? Yeah. So the answer to that has been to look at different profiles of languages that are more efficient, that have certain better guarantees in terms of time to compute entailments. So these are called L2 profiles, and the idea is to define some more efficient sublanguages of L2DL that allow for more efficient reasoning algorithms. One of these we've seen, which is L2RL, which is a restriction that permits rule-based languages. There's L2EL, which is used a lot for classification of ontologies, so ontologies where we have complex terminology, and L2QL, where the idea is that you have a database or an SQL engine. And what this ontology language allows you to do is rewrite your SQL query such that in one SQL query, you can get the answers and all of the answers over the entailments of the database. So the way of reasoning is just you rewrite a query. That's the only thing you need to do. So you take your query, your ontology, you create a bigger query that has lots of unions and so forth. And answering that query over the database is equivalent to getting answers over not just the raw data of the database, but also the entailments. So the community, the description logic community, led a lot of work in that direction later to have more practical profiles. Any questions or doubts? Thoughts? Okay, we're nearly there. So general impressions, there is a big division sometimes in the semantic web community and in different research communities between theory and practice. So the kind of systems oriented people who like to do, build some system, do some experiments to see how long it takes, see if they can optimize that, see if they can make things run faster, get things built, get users on board, usability studies. And the more theoretical people who like to define theorems and prove theorems, they like to show new results, define new languages, study properties of these languages. This exists very much in the semantic web community. There's a lot of tension between these people. And one of the main points of tension in the semantic web community is what direction we should go in for knowledge representation. If we should have something more complex, something more fully featured, something with a more foundational idea, or if we should have something more practical and simple that serves for many use cases. So OWL has been, in that sense, it's widely used. People appreciate it a lot, but there's still some tension in terms of what kind of knowledge representation is really needed for the web, and if OWL is the right way to go, especially the more expressive parts of OWL. Knowledge representation on the web is sort of an open research problem. So essentially, this is something that's still being explored. People are still kind of trying to figure out what's the right answer, and probably we would need a little bit more adoption to be able to understand that, because it would be interesting to see how things develop and so forth. So the schema.org, this Google, Facebook, Yahoo, has some semantics, but it's not so interesting from that perspective because it's centralized. There's like one organization that's doing it. What will be interesting is when different people start defining sort of maybe small ontologies or larger ontologies for their organization or their interests. And then how do you start to connect these? So you start to be able to do some maybe mapping or interoperability across different websites, across different organizations and domains. There's been quite a lot of effort in that in an initiative called Linked Data that we'll see later in the course, which is this way of trying to build upon existing ontologies with your ontology so that you have sort of fragments of things defined by different organizations and people. But there's a lot of kind of open research problems relating to how to manage this and how to manage decentralized ontologies, different websites with different ontologies that might contradict each other and so forth. One of the main use cases for OWL, we're kind of focused on the web and the web of data here a lot, but people in bioinformatics love OWL. So OWL helped them. They had other formats before like OBO, but they use ontologies heavily for the following reason, that in bioinformatics, there's a very technical set of definitions for what it means to, for what are called terminologies. These are sort of terms of art used within the bioinformatics or biology domain in order to organize communication. We don't want people using the same term to mean 15 different things, right? So one example is cold. Cold can mean 5 different things in English in the medical domain. So they want to use codes that are unambiguous and rigorous, and they want to be quite explicit in terms of what they're saying, for example, in healthcare patient records. So if they're taking a history of someone and they want to know what disease it is, they want to be quite unambiguous about what disease they had, what drugs they're taking, what medication they're on. So there's been a lot of work on using ontologies or OWL to represent these terminologies in a machine readable way. And this is called BioPortal. There's thousands of ontologies here that would be typically described in OWL. There might be some in OBO, which is a similar format. And these people, in Germany, I met someone who's working in this area, and he said that basically OWL was a major breakthrough for this community. It was exactly the sort of thing they need. The nice thing in this area is that they already have an existing conceptualization and agreement. They had written it down on paper, and then what they needed to do was to make that machine readable. The problem in many domains in terms of using OWL ontologies is that there's no agreement beforehand. So people need to argue, what is a book? Right? If you want, you could try to have that debate at some stage about trying to formally define what a book is and see if you reach an agreement. You probably won't. What is a movie? Yeah. But in this case, they already had this agreement through various organizations, and they managed to document it through OWL. This is the end of the OWL classes. We still have the last lab to come. where we're going to use a more powerful reasoner for maybe more complex definitions. Then we're going to move on to querying, and then after that we're going to move on to validation and linked data. So this is sort of the end of the knowledge representation section. Yeah, any questions or doubts? You've all suggested papers for the rating group, I guess, or yeah. So yeah, if you have any doubts about the reading group as well, let us know. On Wednesday we can also chat about that. But I guess the main thing is to select your papers. That's the more open part. Yeah, if you already have your papers, that's cool. Okay, so if there's no questions or doubts, see you on Wednesday in the lab. Okay, see you.